Very often in linear algebra, we are concerned with finding the dimension of a vector space. So we're going to spend this video looking at some useful ways in which you can do that. So let's begin with a lower bound for the dimension of a vector space. So what I mean by that is the following. If you have k linearly independent elements in a vector space V, then the dimension of V must be at least k. So for example, if you had 3 linearly independent elements inside a vector space V, then the dimension of V must be 3 or more. And this is actually easy to prove because of what we've seen in the previous videos. So let's say those k linearly independent elements were L1, L2 up to Lk. Then the proof is simply that you know you can always extend a linearly independent sequence to a basis. So L1 up to Lk can be extended, so by adding some more things, to a basis of V. And of course the dimension is the size of that basis, which is at least k. One of the more useful ways to look at this result is actually to think about the contrapositive of it, which is that if you have more elements than the dimension, then those elements must be linearly dependent. So let's suppose we have V be a vector space. Let's let n be equal to the dimension of V, just to save me writing out dim V lots of times. And we'll let V1, V2, up to Vn plus 1 be elements of V, any elements of V at all. They cannot be linearly independent. And the reason they can't be linearly independent is that we've just seen if they were linearly independent, then the dimension of V would be at least n plus 1. In other words, the dimension of V would be greater than or equal to the dimension of V plus 1. This is obviously impossible. So, any time you have dim V plus 1 elements in a vector space, V, you know those elements must be linearly dependent. So, for example, any 3 elements of R squared have to be linearly dependent. If you give me any 3 column vectors of height 2, then no matter what they are, I know they must be linearly dependent. If you give me any 4 elements of R cubed, I know they must be linearly dependent. If you give me 5 2x2 matrices, I know they must be linearly dependent. So let's write that one down. So any 3 elements of R squared, any 5 elements of the vector space of 2x2 matrices must be linearly dependent. And again, the reason is that you know that vector space has dimension 4. So this is very useful because often proving things that are linearly dependent can be a little bit time consuming. You might have to solve a bunch of linear equations. You might have to carefully check that there exists a non-zero solution to a particular set of linear equations, whereas now, straight away, as soon as you see dim V plus 1 or more elements in a vector space V, then you know they must be linearly dependent.